Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. So this is Unit 4 and we're gonna continue to talk about the molecular self-assembly. So this is a molecular self-assembly part 2. So in this lecture, we're gonna talk about a little bit about colloid and then colloidal chemistry. This colloid and then colloidal chemistry is not directly related with pattern transfer, and then only one techniques, the nanosphere lithography, uses this colloid form of nanomaterial. But this colloid is kind of very important in nanotechnology, and then this molecular self-assembly is utilized in this kind of modification of these materials, and then those kind of modification is kind of pretty important. So we will talk about this colloidal chemistry. So today we're going to talk about what is the colloid and then properties and then examples, and then we will also talk about the synthesis of the colloid as well. So this is the nanosphere lithography we will talk about in the couple lectures later. So basically to perform this nanosphere lithography successfully, we should first be able to form this one nice monolayer of nanosphere. And then one of the best way to form this kind of a nice one monolayer of the nanosphere can be done when we modify the surface of the substrate. And then this is one of the type we can use, and then this is another type we can use using this kind of technologies to achieve the nanoscale patterns, and then use this kind of patterns to the further utilization of the following process steps. But again, we will talk about more details about these technologies in the couple lectures later. So what is colloid? The term of the colloidal refers to a state of the subdivision, implying that the molecules or polymer like particles dispersed in a medium. So basically this colloid is made of two phase, and then this subdivision materials is not present as an dissolved form in the medium, but it is small in size, but it is present as an independent phase or material. So these small nanoparticles or colloid just suspended as it is, and then the gravity is kind of it has a much less effect from the gravity, because the surface interaction among these colloids are much more dominant. And then the reason why it can suspend in the medium is because these colloids are moving as a Brownian motion. So that's the reason why it can just keep moving around and then keep suspend into a medium, continuous medium. So this colloid and then the medium can be a combination of three states of matter. So I will show you some of the example of this kind of a colloid and then the continuous medium. So this can be a vapor or liquid or solid. Among them, solid nanoparticle mixed with a liquid medium is the most common example like an gold nanoparticle suspended in the aqueous solution. So that is the one of the example of the colloid. So again, this is subdivision material, which size is kind of much smaller than this continuous medium, is kind of suspended, and then this phase of these nanoparticles, and then this phase of the blue medium can be a combination of all those kind of three phases. So the reason why people are interested in this kind of a colloid or nanoparticle is this kind of structures offer very many unique advantages. So it can be used for scattering the light. So when it is used for a solar cell application, it just working as a plasmonic or photonic effect. So it can just increase the photocarrier generation. And then the particles are subjected to the Brownian motion, so it can be kept suspended in the medium. And then the surface of the charges, we're gonna talk about these portions at the stabilization portion. So those kind of particles without modification may be charged. So those kind of same charges just repulse each of the colloid, so it can just maintaining some distance among those colloids. So these kind of charged particles can be moved or controlled by the external force like an electric field. So this is an example of the colloid. So one of the fog is kind of an example you can see kind of very easily. So fog is one of the example of the colloid. So in this case of that, the air is a continuous medium, and then the small liquid particles is the dispersed phase in this case. And then the nanoparticles, that is another kind of an example. So in this case of that, the medium is a liquid, and then the gold nanoparticle is a solid. This one is an aqueous solution. So to make this kind of a colloid, there are two ways. One is a condensation method. So this is basically using chemicals. It just technically synthesize this kind of a colloid materials. So I'm gonna show you the synthesis process using the videos at a couple slides later. And then there is another kind of a method, dispersion method. That is basically, if this method is bottom up in terms of making small structures from a molecular range of the chemicals, this method is more likely a top down. So I will also show you the way of using this way. So once people just make this kind of a colloid, when people just filtering this kind of colloid, people can make the distribution of the particle size much precisely. So we can use this kind of electrophoresis or other method to do it. So this is the way of synthesizing gold nanoparticles. So in this case of that, we just put chemicals, and then just when those kind of two chemicals make the chemical reactions, actually it just started to those kind of gold atoms just aggregated, and then at some point when it just make certain size, at this size is about made of the 11 atoms. So at this point we call that as an embryo stages. From this point, if we just leave these nanoparticles and just wait, this kind of gold particles just keep added on the surface of these small particles, and then the size is kind of getting bigger and bigger. So that's the one of the way we can synthesize this kind of a gold nanoparticle, gold colloid, using this kind of a chemical reaction. So this colloid can be stabilized as it is synthesized. So as it is synthesized, it can have this kind of negative charges on the surface, and those kind of charges on the surface just to repulse each other. So we call that as an electrostatic repulsion. But in this case of that, somehow, if the condition of the medium is changing, like the pH is kind of pH of the medium is kind of changing, or if some contaminant just added into this kind of environment, this equilibrium can be easily broken. So in the case of that, all these kind of nanoparticles just lose its kind of spacing, and then just immediately agglomerated, and then just submerges to the bottom of the container. So we can modify its surface using molecular self-assembly. So as we discussed in the previous lecture, we can use these kind of molecules. If this purple is a gold nanoparticle, we can use this kind of a small molecules which has an thiol ligand attaches to one end. And then if we mix these kind of small molecules with this solution, if then these small molecules just coated the surface of the gold nanoparticles. So in the case of that, these nanoparticles are much more resistant to the changing environment. So in the extreme case, after we modify these nanoparticles with these kind of small molecules using the molecular self-assembly technology, we can just dry all this kind of a medium material, which is an aqueous solution for gold nanoparticle. So when we need it, when we add another kind of aqueous solutions to the powder form of this kind of nano particles, if then we can redisperse this surface modified nanoparticles, and then we can just have the same well dispersed colloidal solution. But without this kind of modification of the surface, for this case, once these kind of nanoparticles are agglomerated, if then it's almost impossible to make this kind of evenly dispersed solution. So in a sense, those kind of surface modification of these kind of gold nanoparticles make the nanoparticles to be much more stable. So I will show you the video showing the synthesis of the gold nanoparticle. So this video has two parts. So first part, the video shows how to synthesize this kind of gold nanoparticles. And then the second part, this video will show you how to modify the surface of those kind of synthesized golden nanoparticle. So for the molecules we're gonna use to modify the surface of the golden nanoparticle, we're gonna use dodecane thiols, which means it has an 12 carbons and then which has an hydrogen in each of the, and the last hydrogen has a last carbon has a 3 hydrogen, and then in the end there is a thio molecules is kind of attached. So this is the kind of the carbon should be 12. So this is the kind of molecules in smaller version we're gonna use to modify the surface of the golden nanoparticles. So eventually, after the second process, the golden nanoparticles are not dispersed by the electrostatic repulsion, but it is kind of dispersed as a static repulsion. So let's see the video. So after mixing those kind of chemicals, the only thing we need to do is we need to wait uh, the nucleation is happening. So this video, the state of this bottle right now, the size of the golden nanoparticle is kind of bigger than 10 nanometer. When that as it is mixed, it is kind of a much clearer. And then as those kind of a nanoparticle size is kind of getting bigger and bigger, this color of the nanoparticles getting darker and darker. And then it's kind of getting dark, much darker red. So in a sense, it's about bigger than 10 nanometer in size. So after to make the bigger size of the golden nanoparticles, we can just simply wait on the hot plate, and then based on those kind of a color, we can presume what kind of a color will give us what kind of a particle size based on the measurement. And then from this point, as I just mentioned, those kind of golden nanoparticles dispersed in this aqueous solution is dispersed by the electrostatic repulsion. So the surface is not modified yet. So from this point, we're going to apply those kind of dodecane thiol molecules into these golden nanoparticles. So that dodecane thiol will eventually coat the surface of the golden nanoparticles, and then from that modification, those kind of golden nanoparticles will be dispersed as a static repulsion. So this is the process. So after mixing those chemicals and then waiting for this um, waiting for about 5 minutes, we have a phase separation. So this upper red part of the solution has the surface modified gold nanoparticles are dispersed. So this upper part of the solution, the gold nanoparticles are dispersed as a static repulsion. So the later of the video will show you how to forming those kind of one monolayer of the uniform nanoparticles. Since I mentioned this kind of a monolayer formation is the key for success of the nanosphere therapy. So we will see how people are making those kind of a one monolayer of the gold nanoparticle layers on a substrate. So in this demonstration, the original gold nanoparticle is mixed in hexane. So original gold nanoparticle is continuous medium is on hexane. And then for the another kind of a comparison, the second bubble, which is located on your left, that is on toluene. So as we just put those kind of gold nanoparticles dispersed in the hexane into the toluene, those kind of a medium is a form of the mixed medium with the toluene and hexane. So the reason why people try different medium is just comparing the hexane and toluene. Toluene its evaporation speed is much slower than that of the hexane. So based on the different kind of evaporation speed of the medium, we will see how different those kind of monolayer formation would be. So the left bubble, left drop is the medium is toluene and hexane, and then the right drop, its medium is only hexane. So as you saw that when the toluene was used, the evaporation speed is kind of much slower and then controllable. So that is why those kind of gold nanoparticle has a much longer time to align by themselves. So it is much more advantageous for making this uniform color of film. The uniform color means a uniform thickness of the layer. When those kind of medium evaporate uncontrollably, those kind of most of the nanoparticles just stuck in the outside of the ring, and then we call this kind of pattern as a coffee stain. So in this case of that, many portion of the gold nanoparticles deposited in the outside ring. So we wasted many of the gold nanoparticles for this kind of outside of the ring. And then when those kind of particles, those kind of drops getting smaller and smaller as it is dried it, we do not have much nanoparticles left in the middle. So in the middle side, the color of the stain is kind of much lighter than that of the outside. So this means this kind of film is not a uniform one monolayer. Even for this toluene case, the outer side is much darker. So the darker means there are more than one monolayer of the gold nanoparticles present in the outside of this ring as well. So discuss more about the mechanism of this monolayer formation it is this case. So in toluene, this red is a gold nanoparticle. And then as you saw, as this toluene is evaporated, the dimension of the vertical side and then the dimension of the lateral side also reduced. So as the toluene is kind of keep evaporated, the space, the volume of the toluene is kind of getting smaller and smaller. So as those kind of volume of the medium is kind of getting smaller, what happens is those kind of nanoparticles aligned at the interface between toluene and then vapor. And then as the volume is kind of getting much smaller, the density of the gold nanoparticle at this interface is kind of getting much higher and higher. And as those kind of toluenes all evaporated, all these kind of well-aligned gold nanoparticles eventually deposited as a film on the substrate. So this is the way, one of the way, there are three ways people are using to making one single monolayer of the nanospheres on nanosubstrate. But if we have kind of multiple layers in one area and one area is kind of a monolayer, if it is kind of randomly mixed, if then we cannot make highly ordered structures like this. So we should have this kind of one nice monolayer of the nanosphere for a successful nanosphere lithography process, and then we will talk about that in the couple lectures later. So when I talked about the synthesis of the colloid, another way is like a top-down method. We can start from a much bigger version of the material instead of synthesizing those kind of small structures out of much smaller form of the atoms. So so the starting material for this method is a big chunk of the gold bar. So you can see this kind of red smokes is coming out from the gold bar, and then these all red smokes are the gold nanoparticles. And then as you can see, there is a much brighter area, and then these are all the laser beam. So by the residential time of this kind of a laser beam, we might be able to change the size of the gold nanoparticle. But basically, using this way, we can also synthesize this kind of gold nanoparticle out of big bulk material of the gold nanobar. And this is another kind of video, but this video is a little bit different material. So far we talked about metal nanoparticle, so which is an inorganic nanoparticle. But organic nanoparticle is also very important, especially for those kind of biomedical application. This kind of organic version of the nanoparticles are much suitable because body just to accept this type of the organic nanoparticles much easier than those kind of inorganic nanoparticles. So this video will show you how to synthesize those kind of organic version of the nanoparticle. And then this video also will show you a little bit about even how to change or how to modify the surface of the this kind of organic nanoparticle. This is a liposome nanoparticles, and then even it shows how people can make drugs out of this kind of liposome nanoparticles.
Encapsula Nanosciences presents Liposome Basics Part 2. Here we describe the basic methods for preparing and sizing liposomes. The simplest method for preparing liposomes is hydration of dry lipid. The lipid is dissolved in organic solvent along with any lipid-soluble compounds to be incorporated into the liposomes. The solvent is commonly removed by rotary evaporation, resulting in a thin film of dry lipid.
So this part we discussed in the previous lecture. So you may remember the small molecule which is polar and which is non-polar. So as the medium is kind of dried, this kind of polar and non-polar head just aligned, and then it just making bilayer like this.
Solvents can be removed by lyophilization, resulting in a dried lipid cake. An aqueous solution containing water-soluble compounds to be encapsulated is then added to the lipid film or cake to hydrate the lipid and form the liposomes. The aqueous suspension must be heated above the phase transition of the lipids in order for the liposomes to form. The resulting multilamellar liposomes consist of many concentric lipid bilayers. While all or most of a lipid-soluble compound will be incorporated into the bilayers of these liposomes, the amount of water-soluble compound entrapped is usually very low because these MLVs have a small captured volume. Very little aqueous solute penetrates the onion-like layers of hydrated bilayer lipid. The captured volume of these MLVs can be increased by freezing and thawing the liposomes several times. Repeated freezing and thawing ruptures and reforms the MLVs, resulting in an increased number of liposomes with fewer layers of lipid and more aqueous space inside each liposome. Thus, the freeze-thawed liposomes encapsulate more aqueous solute and often have a multivesicular morphology. The aqueous solute is now uniformly distributed inside each liposome. The thin film method is limited to laboratory scale, while the reversed phase evaporation method can be used to produce milliliters up to thousands of liters of liposomes. Lipid is dissolved in organic solvent along with any lipid-soluble components. The aqueous compound is added to the lipid solution. This biphasic mixture is then emulsified by some form of high shear mixing. The organic solvent is evaporated from this emulsion, forcing the lipid into the aqueous phase, where it organizes into bilayers and forms liposomes. Additional aqueous phase is added in order to complete the liposome preparation. Again, the temperature of the aqueous phase must be above the phase transition temperature of the lipids in order for liposomes to form. Unlike MLVs produced from a thin film, liposomes produced by reversed phase evaporation usually have one up to a few bilayers per liposome. Like freeze-thawed liposomes, these liposomes can be multivesicular and have uniform aqueous solute distribution. Liposome characteristics can be optimized for a particular formulation by systematically varying the process parameters. Many variations of these methods are described in the scientific literature. Liposomes produced by these methods have a broad size distribution. The only method which can produce a definable unimodal distribution of liposomes in the 100 nanometer range is high-pressure extrusion through membrane-type filters of a fixed pore size. The stainless steel device which supports the filters used for extrusion withstands internal pressures in excess of 1000 psi. Extrusion cannot be accomplished with standard liquid filtration devices. Larger extruders are pressurized by nitrogen, while extruders handling volumes less than 1 milliliter utilize gas-tight syringes to generate pressure manually. Extrusion must be carried out above the phase transition of the lipids in the liposomes. In order to achieve a narrow size distribution, the liposomes must be passed through the filters 10 times or more. The liposome suspension becomes more translucent during extrusion, indicating that the liposomes are becoming smaller. The lower size limit of a liposome is 30 to 60 nanometers, depending on the type of lipid used. High shear methods are used to reduce multilamellar liposomes to unilamellar liposomes at their lowest size limit. Most water-soluble compounds must be present at the time the liposomes form to be encapsulated. Some ionizable compounds can cross the membrane in their neutral form and be converted to an insoluble salt form inside the liposome. This remote loading technique allows drugs to be loaded into liposomes after the liposomes are formed, but is not widely applicable. Some ionizable compounds can also be loaded into pre-made liposomes with a pH gradient. In this example, the neutral form, but not the charged form of a compound, can cross the membrane into the liposome, but can't escape due to the high concentration of protons inside the liposome. Lipids organize into bilayers due to the presence of water. When the water is removed by lyophilization, the bilayer loses its structural integrity. After rehydration, the liposomes have a different size distribution and have leaked their entrapped contents. Some aqueous solutes, such as sucrose, can replace water at the lipid head group, thus maintaining the bilayer structure when water is removed. In this case, the liposome can be lyophilized, then rehydrated while retaining its original size and entrapped contents. Membrane proteins can be studied in their native state by incorporating them into liposomes. The protein and lipid are co-dissolved in a detergent solution. When the detergent is slowly removed by dialysis, the protein incorporates into the newly formed lipid bilayer. For more information about liposomes, go to our website at www.incapsula.com.
So unlike those kind of gold nanoparticle synthesis, these liposome nanoparticles, when it just dried first, it just becomes a film, and then as we just apply on another kind of solutions and then just heat it up, it just those kind of films just becomes those kind of nanoparticles. So that is why the big difference between this liposome and then the gold nanoparticle is its size distribution is kind of much wider for the liposome nanoparticle. So it needs multiple filtering processes to increase the narrow size distribution. But as to those kind of synthesis of the gold nanoparticles, it just is kind of size distribution is kind of much more uniform without having this kind of filtration. So that's the one of the big difference between gold nanoparticles and then this liposome-based nanoparticle. So just going back to the molecular self-assembly, when we just talked about these specific molecules, we have two places to putting some kind of a functional molecule. So as we discussed in the previous lecture, we use one spot for the ligand. The example is the thiol or trichlorosilane. And then here we can put another kind of a functional molecule like a protein in this case. So in this case of that, as we discussed in that pregnant kit we discussed in the previous lecture, we can just modify this inorganic, in this case of that is a cadmium selenide, but it could be a gold. We can just modify this kind of inorganic nanoparticles to be compatible to the biomolecules. So we talked about the colloid, and then we talked about those kind of a colloid is the combination of any three states of matter. And then we talked about how to synthesize all this kind of a colloid. And we also talked about how to modify the surface of that colloid or nanoparticle materials using molecular self-assembly. So specifically, those kind of self-assembly modified nanoparticles having a static repulsion, so it is kind of a much more resistive for an aggregation, and then even we can dry that colloidal solutions, and then when we add new solutions, we can redisperse this kind of a static repulsion, those kind of nanocolloidal solutions using the static repulsion. So this is the discussions about the molecular self-assembly, and then from the next lecture, we're gonna talk about local polymer therapy. Thank you.